All right, so in any event, we see left and right flow boundaries. Okay, this is again this is just a detail of your 30 box model, showing you once again in detail that the faces, nothing is sequential. You've got face 41 between box 5 and 15. And so you're going to need a map file, something like that. Anything else here? Okay. Let's see. Okay, so. Okay. Recall that I said that you have to provide information from two places. There's what I'm going to call invariant information that very often will come from a model input file, like what we call a geometry file or a map file. And then there's, information that varies, like the flows or the dispersion that has to come from some hydrodynamic file. So the if you will, what never varies, I'm going to go over, is the cell surface area. Okay, so now imagine we've got all these boxes connected. From the top to the bottom, if you will, take a column of boxes. That column, the surface area, never changes. And this is an important point to remember, okay? So a column of boxes, for example, will not taper down. The column of boxes does this. If you want to have a taper, so to speak, what you do is you have fewer cells, in any event, let me just say that the surface area is invariant. So you put that in once, and it holds for all cells in that column. The cell length, the box length in the X and Y direction. The box length in the X and Y direction never changes. Okay? When you say how long a box is, how wide a box is, it is. It will never change from the initial value. The number of surface cells, is something you have to provide to the model. How many surface cells? Once you specify that, it never changes. Cells don't come and go. If you have 11,000 cells on the surface at the beginning, you better have 11,000 when you're finished. The flow face area. That's the cross-sectional area of a cell, if you will. We're going to talk about this in detail. The number of horizontal flow faces. We have flow faces in the horizontal directions. We have flow faces in the vertical. So the number of horizontal flow faces is something you specify once. It's an index. Just when we go to solve the conservation of mass equation, you're going to go from 1 to the number of faces. Okay, so that's something you have to provide. You provide it in the control file. The total number of flow faces, that's the horizontal plus the vertical. We could have just said, what's the number of vertical faces? Lost in the sands of time is why the fellow who coded it did it this way, but you need the number of horizontal faces and you need the total number of faces. And if you looked at the code, what you'd see is when you do the vertical, you go from NHQF plus 1 to NQF. Basically, you run through the array of vertical faces, but in any event, maybe I'm getting too... HMBV is the box volume. It's the volume of cells below the surface layer. And then the volume of cells in the surface layer. Now, okay.
Question again. I'm sorry to be keeping asking.
No, well, ask.
Area, I could see that being constant, unless you're talking about, otherwise it'd be surface area, below the surface, but your surface steps are varying, so shouldn't that surface layer will vary? Okay.
It will vary.
So that's maybe the surface area like mean tide or whatever.
let's see now.
Or,
Let me
well,
back up.
whatever type
The
it is.
surface area will never change.
Well, I'm
The
sorry,
cross-section.
flow face areas.
Yeah.
Below the surface area doesn't change, but your surface is going up and down.
So that will change, and that's why, I guess it says invariant hydrodynamics.
Oh, invariant height. Okay, sorry. Right, okay.
But it's a good question, and I'm going to have to go into this in a minute or two, so, you know, get it now. Like I said, I haven't done this lecture before, so things don't all come out in the order in which we wanted to come out, but hopefully we get the things. Go ahead, Louis.
This is a load question to the surface. So atmospheric deposition would be a surface load, and I think the way we specify it, correct me if I'm wrong here, is that the surface area is the orthogonal cell surface area. And so we have to make sure that the actual tidal water surface area is, we specified the load to the actual tidal surface area, and there's ways we can do that, but I think that's a necessary trick that needs to be applied.
Actually, Louis, I think you folks give me the kilograms load to each cell. So you've taken care of that before me. I digress, small digression. Think of, Lewis is talking about atmospheric loads. Now, typically an atmospheric load would be something like grams per square meter per day. And, you know, if the cells have different surface areas, then the loads to each cell are going to be different because grams per square meter per day over so many square meters differs. And Lewis is wondering how we account for that. And actually, the Bay program has those cell surface areas, and they take care of it before I ever see it. So all I see is grams per day to each cell.
Right, per day. So the essence of the question is, the surface area is not the actual tidal surface area of the cell. It's the surface area of the orthogonal cell. Is just a distinction to be made.
But if the lengths in both directions never change, which they are invariant, and they would be invariant even in a regular hydrodynamic model, that surface area doesn't change,
Oh, yeah,
right?
right.
Okay, so then you could have done it either way.
Yeah.
Actually, there is an option to do it that way. I'm not going to talk about it today,
Right.
but you can indeed do it that way. Okay. This is actually extracted from the code. So, and those of you who are going to try to link to other models than CH3D, or, you know, who are actually going to be using a hydrodynamic model. So you see we read in the surface area, and we only have to do that for the number of surface boxes, because remember, once you have the surface area in the surface cell, it carries to all the bottom cells. The box length in X and Y direction, the area for the horizontal flow faces, we'll talk about this in the middle. The hydrodynamic box model volume and the surface box volume. We'll talk about this in a couple of minutes, but in any event, okay. Here are the things that here are what define the time variable hydrodynamics. The horizontal flow faces and the surface layer, the dispersion, the flow, and the distributed flow. Interesting, okay. Faces, dispersion, flow. I'm getting a little bit, okay. We're going to stop here for a minute. Now here's where we're going to, okay. Okay. Let me ask, before I go really in more depth, up to now, are there any questions? Okay. So,
So this model does not allow you to add or reduce?
No, do not.
Once you have that, it's just a change in the surface layer thickness.
Okay. Here, this is for, now, okay, so before we had the stuff that doesn't vary in time. Now we have what does vary in time. So now this is what Jim was talking about, and I'm going to get on the blackboard in a minute. This is the area. This is the cross-sectional area, the longitudinal and lateral, and you'll see that, and this is what my friend was just talking about, the index is from 1 to the number of surface flow faces.
Okay, that's how you do it.
So what's happening is, and I'll show you on the blackboard because I neglected to make up a slide on this and discovered it as I was going over the lecture. Below the surface layer, what the hell, let's do it now. I hope the camera catches this because you want to get this. Our hydrodynamic model is what's called CH3D. Okay. CH3D uses what we call a, I'm going to call it a Z-grid approximation. Now, what we mean is the way we represent depth is to vary the number of boxes in a column. Now, this is different from, many of you are probably used to now what's called a sigma grid, in which case the number of boxes in a column is constant, but the thickness of the boxes varies. So let's do this. So what CH3D does is something like this. We should photograph the blackboard, but in any event, this is CH3D. We're looking at an elevation. So what you see is in order to vary the depth, we vary the number of boxes, okay? This is in contrast, like I said, for a lot of you, and I think people who use ROMs or EFDC, what you have is a sigma grid. And what you've got is you've got the same number of boxes or same number of layers everywhere. But what you do is the thickness of these layers varies as you move. So the way you represent changes in depth is by the thickness of the layers. Okay, so there's a difference between now. Tide goes up and down. How do these two grids handle these things? Tide goes up and down. In CH3D, the surface layer, goes up and down. So the way tide is taken care of is we change the thickness of only the surface layer. Only. These other cells, the subsurface cells, do not change thickness. And that's why it wasn't apparent here, or maybe it's confusing, but that's why for these subsurface cells, you only have to read the geometry, for example, the cross-sectional areas one time, because they never change. The thickness never changes. If we were working, so this is the only one that changes. So that's why if you look at the first line up there, read height area 1 through number of surface flow faces, NSQF. So every time you read in new hydrodynamics, you have to read in the cross-sectional area of these faces. Because as the tide goes up and down, those faces change. But you don't have to read in, you read these other cross-sectional areas in once when you initiated the model. Once is enough, because they'll never change again. Diffusion coefficient, well, we'll get into a couple more. Now you see there's, go to the third line, HMSBV. That's the surface box volume. That's the volume of these surface boxes. Okay? You don't need to read in the volume of these boxes because you read it once, it doesn't change. It's always constant. You read in the flow, you need to read the flow in at every face, because even if the geometry of these cells doesn't change, the flow across these faces is going to change. So you read the flow in for all the horizontal faces. Then you read in the flow for the vertical faces. And as I said, it's just the way this is done. We could have numbered the vertical faces separately, but we go from the number of horizontal faces plus 1 to the total number of faces. And again, we're reading in, you know, the flows across these vertical faces change. I don't know if I want to talk about this or not. There's a, all right, well, I should mention it, you know. If you think about, let's think about Chesapeake Bay. There are flows that come into, along the perimeter of the bay, there are flows that come into every single cell which adjoins a solid boundary. We don't want to have to specify, make a boundary condition at every single cell that adjoins a solid boundary, okay? And we don't want to then go to the problem or the headache of specifying boundary conditions, concentrations at every single one of those cells. So what we have is something we call literal flows. Literal flows are flows which can enter a cell but not through an open boundary condition. So let me draw another drawing. What the heck, right? So this is a very abstract Chesapeake Bay. Up here at the Susquehanna River, that's an open boundary. And we specify the boundary condition flowing in. The Potomac River, that's an open boundary. We specify the boundary conditions flowing in. But you've also got all these tiny little flows along, you know, the whole boundary of the system. And we don't, as I said, we don't want to go to the trouble of specifying boundary conditions for each one of those. So we call these literal flows. And they come, you know, they come from the watershed model. And, you know, we read those in. But, you know, it's a simpler way of dealing with the fact that there are, in fact, I don't know, there are several thousand of these flows that adjoin the boundary, and we just don't want to deal with it. So we have something we call literal flows. Go ahead, Jim.
On the little, suppose you had you have a significant wastewater treatment plant. You can either put it in as a boundary, perhaps, but suppose it was the diffuser into the middle of the bay. Could you put that? Would that be where you would put that in? As
you could put it there.
Just put it into wherever cell goes in. Okay.
You could put it there also.
Right. Okay. So it's a literal and diffusers or whatever.
Yeah.
Okay.
Yeah. Yeah. Well, let's see. Let's look at that little.
Sorry, just reading the literal flows. Which line is that?
QLit.
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 You can only read literal flows from 1 to NB, which I presume are the number of boundary.
NB is number of boxes.
Oh, so it's for all of the boxes.
There you go.
Okay, I knew that.
Okay.
Carl.
Yeah.
So you could read a literal flow for any box.
Yeah. And actually, you're compelled to specify them for all boxes, but if they're zero, yeah, they would be zero.
Do you allow like multiple flows to one box specified separately?
No. Nobody's ever asked that question, but you know.
Like you have some, you know, this big box, you have wastewater going in, you have tributary going in, you have stormwater going in. So you have to sum it up.
If you treat it as a literal flow, you have to sum them up. That's correct.